Welcome to this course of the heat transfer. Let us explain first what is the definition of the heat transfer. And the heat transfer can be defined as the subject that dealing with the transmission of energy from one region to another region. Beside that, this definition, there are three types of heat transfer that transfer from one region to another region. For example, as I mentioned before, the heat transfer is a subject that very important in the thermal sciences and the field of engineering related to the thermal sciences, especially mechanical engineering, chemical engineering, air conditioning, power field, aerodynamic field. So that this course will cover this topic of the heat transfer. So that the heat transfer actually transfer from one region to another region. And the heat is transferred by three types or three modes that we will explain them in this course. The first mode of heat transfer is called as conduction heat transfer. The second is called as convection mode of heat transfer, and finally the radiation heat transfer. For the conduction heat transfer, imagine that there is a wall, for example this wall, and let us say that this wall have some thickness, for example its thickness, for example 2 millimeters, and there is a heat source, or this left side wall is maintained at temperature T1, which is higher than the temperature of the right surface. T1 is higher than T2. Okay, so that according to the heat transfer definition, the heat will flow from the region of high temperature to lower temperature. So that if I have a solid wall and this material of course have a thermal conductivity, I will explain this property very soon, so that the heat transfer will drop from this region of high temperature, for example this temperature, for example 100 Celsius, and this temperature is 25 degrees Celsius, so that we will see that there will be a drop in temperature. You can do experiment for this conduction heat transfer easy in the laboratory. You can install here a temperature recorder like thermocouple, and you can measure the temperature, and you will see that there will a drop in temperature if this left side wall is maintained at temperature higher than this. So that this is the first mode of the heat transfer. And the convection heat transfer let me illustrate very important point. In the conduction heat transfer, actually the heat transfer by conduction is occur in a solid, for example in materials or on composite wall. Okay, regarding the convection heat transfer, actually the convection mode is in which the heat transfer is transferred by fluid mixing with one portion of the fluid or with another. For example, imagine you have a circular pipe, and there's some working fluid flow inside this pipe, and I am sure that you treat with and dealing with this problem in the fluid mechanics, this is the center line. If you remember in the second year that the college study the fluid mechanics, you learn how can you calculate the friction factor, the Reynolds number, and you know how the flow is laminar or turbulent based on the value of the Reynolds number. We will illustrate this topic of the convection heat transfer, and we see a lot of topics that connect between heat transfer and the fluid mechanics when we treat with a convection heat transfer. But as a beginning, the convection heat transfer occurs between the fluid flow in touch with a solid, for example internal pipe flow or external flow. For example, if you have a flat plate and there will be some fluid flow over this flat plate, you will have here temperature boundary layer and thermal boundary layer, which illustrate that the heat transfer is occur due to the temperature difference and the flow of the fluid. So that this is called convection heat transfer, in which the heat transfer is between the fluid and flow inside the pipe or over bodies. When we applied some heat source, for example, if this pipe, if we applied a heat flux to this pipe, then you can see that there will be a heat transfer due to the convection, not conduction, because here we have fluid. Finally, the radiation heat transfer. Radiation heat transfer actually is the transfer of heat through space or matter by means of by mechanism other than conduction and convection. And we will illustrate in the radiation that there is an electromagnetic field, or actually it is a quanta, which is an emission of the same nature as light and radio, which is the final modes of the heat transfer, which is the radiation. We illustrate it in the final course of this heat transfer course. So that let us start in this course by explaining the conduction heat transfer. We first will illustrate on the here we will illustrate the conduction heat transfer. As I mentioned before, the conduction heat transfer occurs in the materials or in the solid when some wall maintain at the temperature T1, which is higher than T2, so that the heat will flow in this direction. Okay. Now, actually, the governing law or the governing equation for the heat conduction is very famous, and it is known as Fourier law. Fourier's law illustrates that actually it is empirical law and made on observation, so that actually if we have a solid wall have some thickness, for example, its thickness or its length is L, and the heat transfer will flow in this direction because the T1, which is maintained, for example, at 100 Celsius, is higher than T2, which is kept at 25 degrees Celsius, so that the temperature will drop, okay, so that we will have a decrease in the temperature. And for this relation, Fourier illustrates that the rate of flow through a homogeneous solid material is directly proportional to the area of the section at right angle to the direction of the heat, which illustrates that the heat, which is this is the heat flow, is directly proportional to the area and the temperature gradient. Because this T1 is higher than T2, so that we will have a gradient along the length of the plate, dx, okay? X actually measured from this. And the proportional constant is known as K, A dt by dx. So that K is nothing but a constant of proportionality, which is known as a thermal conductivity, which is very important thermophysical property in the conduction heat transfer. For this, actually, we have here a negative sign, and the negative sign illustrates here that there will be a decrease in temperature, okay? So that temperature gradient, the temperature gradient dt by dx is always negative, and we put this negative in order to have a positive Q. So that this is known as Fourier's law, which is very important in the conduction heat transfer. So that it is easily, Fourier law is nothing but if you have a wall maintained at a temperature, at a different temperature on the left and the right wall, and this will have some thickness, so that the heat flow from higher concentration of temperature to low concentration of temperature can be expressed by this relation, Q equal minus K A dt by dx. But I would like to inform you that area here actually is not L by this length, okay? Actually, the area here is, let me draw the isometric view of this wall. It will be something like this. and the heat transfer, the heat flow from this direction, so that let me show you the hidden lines. The area here, when we say that Q equal to minus Ka dt by dx, area here is not this length, for example, let this L and this H is not L by H. Actually, the area is this wall that make right angle with the flow direction of heat, so that the area will be this, okay. For this reason, the area actually is make angle 90 degree with the direction of the heat, which is this. This is very important, and when we solve mathematical problem relating to this topic, I believe that it will be very clear. So that let us complete now, and let us explain the unit of the thermal conductivity. As I illustrate that Q, according to the Fourier's law, is minus Ka dt by dx. Now, we know that this is a Q, and the unit of the Q, which is the heat transfer, is watt. K, the unit of the A, which is the area, is meter square, okay? And this is actually K is not Kelvin, it is K. I wrote it K, which is the thermal conductivity. I would like here to find the unit of K, which is the thermal conductivity, so that the unit of the Q is watt equal to K. The unit of the area is meter square, and the unit of the temperature is Kelvin or Celsius, for example. You can write it as a Kelvin, but I write it as Celsius to distinguish it between K, thermal conductivity, because you know that the symbol of the Kelvin unit of temperature is K naught, and Celsius temperature, Celsius scale is C, denoted as C, so that I write the unit of temperature here as C Celsius to distinguish it between the K. Okay, divided by X, and we know that X is the length of the wall, so that its unit will be meter. Now I would like to find the unit of the K, so that I can further simplify it. K, this can be cancelled with this, so that here I have M multiplied by Celsius. In this way, we can write that the unit of the thermal conductivity is watt per meter Celsius. This is the unit of the thermal conductivity, watt per meter Celsius. It is very important actually to know the unit of each term in the Fourier law, so that the unit of the Q is watt, and the unit of the K is watt per meter Celsius, and unit of temperature, as you know, is Celsius, and length is meter. So that we can write that K also watt per meter Kelvin. Okay, because the relation between the Kelvin scale of temperature and Celsius is nothing but added to the Celsius 273, so that we can write it in terms of Kelvin or Celsius scale. Now this is the thermal conductivity, actually is very important, and in the mathematical example of the heat transfer, it will given for you. For example, the thermal conductivity will be known value, okay, known value. For example, the K, which is the thermal conductivity of air, for example, is about 0.024 watt per meter Kelvin. And in the conduction heat transfer, we are interested in the K of the material, so that the material, for example, if we have nickel, for example, the thermal conductivity of the nickel is about 93 watt per meter Kelvin. You don't need to save the thermal conductivity of materials, as it's given for you, and there is standard tables for the thermal conductivity. The thermal conductivity property will be also very important when we're dealing on the convection heat transfer, not only on the conduction. So that here let us focus at this moment on the thermal conductivity of the materials. Besides that, the thermal conductivity can be as a function of temperature, which is K naught 1 plus beta T. so that the thermal conductivity may be uniform or constant value, like thermal conductivity of the nickel, or maybe as a function of the temperature. So that let us take a simple example that illustrates the Fourier's law. So that let us say that we want to calculate, for example, calculate the rate of heat transfer rate. Okay, actually the heat transfer rate is different from the heat transfer. I will illustrate that for you. When we say heat transfer, then we mean Q only, and its unit is watt. But when we say heat transfer rate, then its unit will be watt per meter square. So that this is a heat transfer rate, is the watt per unit per meter square. Okay, the heat transfer rate is nothing but the heat transfer per unit area, and this is very important when you apply the Fourier's law. So that we need to calculate the rate of heat transfer, okay, per unit area through a copper plate, 45 millimeter thickness, whose one face is maintained at 350 degrees Celsius and other at 50 degrees Celsius. So that let us convert this physical meaning of the problem into a schematic, simple schematic diagram. The problem illustrates that we have a plate made of copper, okay, and one of its surface, for example, let us assume that the left surface is T1, is maintained at 350 Celsius, and the right surface, which is T2, which is kept at 50 degrees Celsius. So that according to the definition of the heat transfer, which is illustrate that the heat transfer is a subject dealing with the energy transferring from one region at higher concentration to lower, so that we will have here a temperature gradient from this surface, which is kept at a temperature higher than the right surface. And now the thickness of this surface, which is, for example, L, you can write it as X, there is no problem, which is 45 millimeter, which is 0.045 meter. We convert it into meter. So that as we mentioned, this is made of copper. So that take the thermal conductivity of the copper, which is denoted as K of the copper, as 370 watt per meter Celsius. So that now let us show. Let us illustrate the first thing. This is a problem belong to conduction or convection or radiation. As I mentioned, when the heat transfer is in solid materials, then conduction heat transfer will be dominated, so that we will solve a conduction heat transfer. Now, for the conduction heat transfer, we know the governing equation for the conduction heat transfer, which is Fourier's law. So that as a beginning, we write the Fourier's law, which is Q equal to minus K multiplied by area multiplied by the temperature gradient dt by dx. Now, after that, Q equal minus Ka dt by dx. Now we want to find the heat transfer rate, and as I mentioned, the heat transfer rate is actually nothing but a Q per unit area, so that I will transfer the area to be denominator of the left hand side, so that it will be Q divided by A equal to minus K minus K dt by dx. all I have making here is that I transfer A to the left hand side and I write Q per unit area, which is denoted as heat transfer rate, so that the heat transfer rate actually is nothing but a Q per unit A. So that after that Q double prime equals minus K dt by dx. Actually, heat transfer rate is also known as heat flux. Okay, heat flux, which is also watt per meter square. Now let us complete with solving the problem. After writing the Fourier's law, heat flux equal minus K dt by dx. Now the theorem of conductivity is given in the question, and delta T dt can be written like this: minus K, this will be T2 minus T1 divided by the length of the plate, which is this. This is the length that separates this surface, which is maintained at this temperature, and this temperature, so that it will be L. After that, I will distribute this negative sign so that I can write T1 minus T2, because this minus will be minus T2 plus T1 divided by L. Now, this is the heat flux, which is known as the heat transfer rate. Is actually the thermal conductivity is given, which is a 3.7 multiplied by T1, and T1 is this. T1 is this, is 350 Celsius, so that minus 50 Celsius divided by the length of the blade. The length of the blade is given in millimeters, so that I convert it in meter, okay? Because the unit of the copper, of the thermal conductivity of the copper, is in meter, so that it will be 0.045. After that, I can solve it. This equation, we can use the calculator, which is 370 multiplied by 35 minus 50 divided by 0.045. The answer will be this. Let me show you how can I write this number, which is 2466.667. This will be in watt per meter square. This can be written as 2.46 multiplied by 1, 2, 3, 4, 5 multiplied by 5 10 to the power 5 watt per meter square. This is the heat flux, which is 2.46 multiplied by 10 to the power 5 10 to the power 5 watt per meter square. This is the heat flux, which is in watt per meter square. Okay, let us check the unit. For example, we know that the thermal conductivity unit is watt per meter Celsius, and the temperature unit is Celsius, okay, and the length is meter, so that this Celsius can be cancelled with this, and this way I have watt per meter square. Okay, sorry, I made mistake here. 246. This will be 6. Okay, so that this will be to the power 6. Okay. After that, you know that this unit, okay, can be written as Q double prime. Okay, a 2.46 megawatt per meter square. In this way, you know that megawatt is nothing but 10 to the power 6 watt. This is unit conversion, is very important. In this way, we find the heat flux, and we indicate that the heat flux is watt per meter square, which is the heat transfer rate, which is Q divided by A. heat transfer per unit area. So that this symbol or this nomenclature, heat transfer rate or heat flux, is very important in the heat transfer literature. In this way, we illustrate how can we use the heat transfer by conduction, which is governed by the Fourier law, so that we, in order to find the heat transfer through a wall, through a material. Now let us taking the governing equation of the heat transfer due to the conduction. So that, as I mentioned, we will first focusing only on the conduction heat transfer. We will treat about the convection in another time, conduction heat transfer, so that when we are studying the heat transfer, it is very important that we should keep in our mind we have to know some physics and some mathematics, because the heat transfer actually is a combination of the physics and mathematics. So that now we will focus about the conduction heat transfer. As I mentioned before, conduction heat transfer will be in the solid materials, okay? There is no fluid, so that it will be conduction heat transfer. Even if we have some fluid, for example, this is a problem when we have some air gap, and this air gap, which is here, this air gap, and here we have some convection environment, and for example, this kept at high T1, which is 100 Celsius, and this kept at another temperature. We have here also a convection environment. This is solid, and this is air, which is the working fluid, so that we will treat about it later. But now let us find the governing equation of the heat transfer by conduction, also known as diffusion, which have the same meaning. So that, let me firstly, when we treat with the conduction heat transfer, that we should keep in our mind that there are three types of the coordinate, which is the Cartesian coordinate, also there is a spherical coordinate, okay, and there is a cylindrical coordinate. Now, firstly, let us treat with the Cartesian coordinate, because the same procedure for the Cartesian coordinate will be applied for spherical and cylindrical. The only difference will be on the Cartesian, on the direction. For example, in the Cartesian coordinate, the coordinate will be x, y, and z. Now, the governing equation, and this is very important, the governing equation of conduction heat transfer is this: del square T plus Q divided by K equal 1 by alpha shall T shall tau. This is known as the general, this is the Q sub G, heat generation. This is the general heat conduction equation. This can be written like this: del square T, I mean it shall square T shall x square, plus, since I have x, y, z, then I have shall square T shall y square plus shall square T shall z square equal to, plus heat generation term divided by thermal conductivity equal to 1 by alpha. Alpha is a thermal diffusion, and this term is actually very important when we dealing with the convection heat transfer. It is actually very important on the convection, higher than the conduction, multiplied by shall T temperature divided by shall tau, this mean time. Okay, so that let us explain the following. This is a temperature, and this is the coordinate x, y, z. This is the heat generation term, thermal conductivity, thermal diffusion, temperature, time. Okay, so that when we say, or when we write shall T shall tau, we mean that the temperature change with time, so that this is actually the unsteady term or transient term. Okay, And now this means that the temperature change in the x, y, and z. Okay, the temperature changing with the three coordinate x, y, z, and with time also. Okay, so the temperature will be as a function of x, y, z, and temperature. And this is the heat generation term. In this way, we want actually. And first of all, when we dealing or study the heat transfer, it's very important to know the governing equation, and also how can we derive this equation, so that the derivation of the general heat conduction equation is actually very important, so that the derivation in the next section of this lecture will illustrate the derivation of the general heat conduction equation, but in Cartesian coordinate. Now this will be illustrated in the present lecture, so that let us find how can we derive the heat conduction equation. Actually, if you remember, in the subject of thermodynamics, there is a control mass and there is control volume. Okay, actually each problem in the heat transfer and the fluid flow and thermodynamics can be solved considering either control mass or control volume, and it is very important to decide if you solve your problem using control mass or control volume, so that in the heat transfer we actually, and the fluid flow, we actually using control volume, so that all I have to do now is that I will make a control volume and apply energy balance, so that a major objective in the conduction analysis is the temperature field, because as I mentioned before, we are interested in the temperature distribution, so that we need to develop a relation of temperature, as I mentioned here. Okay, temperature actually here is a function of x, y, z, and as a function of time, so that the temperature distribution is our objective in the conduction and the heat transfer. Okay, so that all we have to do now is to take a control volume. In this way, let me say for that. I will draw a control volume which is this. Okay, I will show you now the header line. Now let us illustrate our direction. This is x, z, and this is y. Okay, we have x, y, and z. As you know, this is the q in the x direction. Okay, so that here we have a differential, we will take a differential term, so that this will be dx and this will be dy, okay, and this will be dz, so that let me write it here, dz. Now according to the Taylor series, if this is a qx, then this will be qx, q sub x plus dx. And now if this in this direction, is what is z, so that this will be qz and this will be qz plus dz. And finally this will be q y and this will be qy plus dy. And according to the Taylor series, this is a very important subject. You can take a review about the Taylor series in the mathematics. According to the Taylor series, let me just illustrate for you the topic. If temperature x plus dx, okay, we can write it as tx, okay, at point x plus delta x divided by 1 factorial shall t shall x plus dx square divided by 2 factorial shall square t shall x square plus dx to the power 3 divided by 3 factorial. We can write it d, okay? There is no problem. Or delta. Shall to the power 3 shall x to the power 3 plus till we get dx to the power n divided by n factorial shall x. Okay, so that here actually in the heat transfer we're taking only to this term, to the second derivative. In this derivation we will take till the first derivative, so that q x plus dx, if this is temperature x plus dx or dx, okay, then qx can be written like this: q sub x plus shall x for qx dx. Okay, I transfer this term here only. Okay, similarly qy plus dy will be q sub y plus shall y q sub y dy. Similarly q z plus dz will be q z plus shall z qz dz. Okay, in this way we find qz plus dz, qy sub plus dy, and qx plus dx. After that, actually, there is, as we know from the thermodynamics, there is heat generation, okay, inside the material, okay, Q generation, and also there is energy storage, which is the internal energy storage inside the material. So that it is very important to include not only the heat transfer in the body and leave the body, but also the heat generation within the body and its internal energy. So that all we have to do now is to make energy balance. Okay, and when we say energy balance, we mean by this actually the energy in to the body, which is a qx enter, okay, the qz and the qy, okay, and plus internal energy, okay, generation, heat generation term, okay, minus energy leaving the body out, okay, equal to the energy storage in the body, okay, because energy out, we mean that qz plus dz, qy plus dy, okay, so that I transfer to this side, okay, so that I can cancel some term as I illustrated soon. So that let me illustrate for you that EST, which is the storage, energy storage, is equal or obtained from rho Cp, which is the specific heat at constant pressure. Okay, this is the same property that you take it in the thermodynamics. Shall T shall tau multiplied by the volume dx, dy, dz. And there is also energy source associated with the rate of thermal energy generation, which is E sub G, okay? Equal to the Q dx, dy, dz. Now all I have to do now is to substitute in the energy balance, okay, energy equation, the heat flow in and out, okay, and added these two terms of the thermal energy storage and the heat generation in the body. And after that, let me show you what we will get. I will rewrite again here, okay, this is, okay, now energy in, the energy in, let me write it again, E in plus E generation minus E out equal to E storage. Now, the energy into the body, the heat flow is Qx, as you can see that this arrow is enter, the Qy is enter, and Qz, so that here I will write a Qx plus a Qy plus a Qz. Plus the heat generation term, which is this, Q dx, dy, dz, will be Q dx, dy, dz, minus the heat generation that leaving the body is Qx plus dx, which is this, okay, qy plus dy and qz plus dz. So that let us first only write them qx plus dx minus, because the sign here is not minus, minus qy plus dy minus the qz plus dz equal to rho cp shall t shall time dx dy dz. Now we can write it as follow. I will write them here: qx plus qy plus qz plus the heat generation term q dx dy dz minus a qx plus dx is this. Qx plus dx is this, okay? So that I will open a bracket, I write qx plus shall x qx dx minus qy plus shall y q sub y dy minus qz plus shall z q sub z dz. Okay, so that all I have to do here is that I substitute qx plus dx, qy plus dy, qz plus dz in the energy balance term equal to the thermal energy storage is rho density multiplied by the specific heat at constant temperature multiplied by the temperature variation with respect to the time multiplied by the volume of the control volume, which is dx, dy, dz. Now, I can, as you can see here, I can distribute this negative sign on this, okay, on this, so that I will rewrite them in this way. We will have the following: qx plus qy plus qz plus heat generation term, which is dx, dy, dz minus qz, qx minus shall x qx dx minus qy minus shall y q sub y dy minus q sub z minus shall z q z dz equal to rho cp shall t shall tau dx dy dz. Now we can cancel the qx with the qx, qy with the qy, because you can see the sign here is positive while here is negative, minus a q sub z minus a plus, okay? In this way we can write that this will be after cancelling q at the inlet, this will be minus shall q sub x shall x dx minus shall q sub y shall y dy, okay? I write only this term, okay? Minus shall q z shall z dz plus q dx dy and dz equal to the rho cp shall t shall tau dx dy dz. Now let us find qx, okay? We need to find the qx, okay, and the qy and the qz, so that let us, this equation will be equation 1, for example, okay? Let us find the qx, okay? And we can find the qx according to the Fourier's law, okay? Qx, or generally q, according to the Fourier, is minus k multiplied by the area that make 90 degree with the heat flow direction multiplied by shall t shall direction, for example, in the direction that we, for example, in x, okay? In this way, let us, this is a qx. Now, so that here, you can see here that this is a qx, okay? I want to locate the area. The area, of course, is not dx multiplied by this, okay, by dz. The area that make 90 degree with the heat flow is this, and this area will be this, which is dy multiplied by dz. Okay, this area dy dz will make the 90 degree, so that I will write it minus k dy dz shall t shall x. Using the similar techniques, we can find that qy will be minus k dx dz shall t shall y, okay, and the q sub z will be minus k dx dy shall t shall z. Okay, you can see here that qy, this is the area that make 90 degree with the flow direction, so that if this is a q in the y direction, the area will be dx multiplied by dz. Regarding the dz, which is a flow from the bottom to the top, the area will be this, dx multiplied by dy. I hope that this is clear. Now after that, after I find these, all I have to do is to substitute this, okay, qx, qy, and qz here, this here in equation 1, okay, so that shall x will be for qx, okay. Let me explain it. Now I can write that minus shall x for qx, qx will be minus k shall t shall x dy dz multiplied by dx, okay. Similarly, minus shall y for q sub y, which is this, minus k shall t shall y dx dy dz, okay, because this is dy will be added to dx dy dz, minus shall z for qz, which is minus k shall t shall z dx dy dz, minus the plus the heat generation term, which is q multiplied by dx dy dz equal to rho cp shall t shall tau dx dy dz. Now we can canceling, okay, dx dy dz, okay, as you can see here, dx dy dz can be cancelled from each term in this way, and this is a negative sign can be multiplied by this negative sign, so that it will be converted into positive. In this way we can write this shall x k shall t shall x plus shall y k shall t shall y plus shall z k shall t shall z plus the heat generation term q, okay, equal to rho specific heat at constant pressure shall t shall tau. Now this is called as the general heat conduction equation, okay, for unsteady, okay, with internal heat generation, okay, and the three-dimensional, okay, x, y, z. There are some simplification that we generally make it. For example, for uniform thermal conductivity, if K is constant, okay, is constant, okay, in this way it can be written out of the differential sign, so that I have here K shall x shall t shall x plus K shall y shall t shall y plus z shall z shall t shall z will be plus q equal to rho cp shall t shall tau. Now dividing by k, okay, I will divide it each term of this equation by the thermal conductivity, and we know from the mathematics that shall x for shall t shall x can be written like this: shall square t shall x square plus shall square t shall y square plus shall square t shall z square plus Q divided by K equal to rho Cp divided by K shall T shall tau. Now we study the convection heat transfer, we will illustrate that alpha is actually K divided by rho Cp. This is actually known as the thermal diffusivity, which is very important property. Okay, in this way I can write this is actually rho Cp divided by K, and alpha is the inverse, so that I will write 1 divided by alpha. In this way I can write shall square T shall x square plus shall square T shall y square, and the temperature variation with the Z plus the heat generation term will be 1 by alpha shall T shall tau. So that if we want to describe this equation can be described as follows. This is nothing but the general heat conduction equation in a 3-dimension x, y, z with internal heat generation, okay, under any steady state, okay, because the